Okay, so welcome everyone. This is the week 7 webinar. So we're now, back to, past half the class now. So we're moving forward, and it's an odd week. Odd weeks means that you don't have to worry about the exam because I do it on even weeks, and that seems to work. I've tried something different before, and that people like this way better. So hopefully it works well for you. And again, this is Tuesday at noon because even though we had it Tuesday last week, because I didn't want to make you guys, come to or even suggest you come to a webinar on Halloween night, because either you have kids and you're trick-or-treating with them, or you're opening up the door for kids to, give them candy, one or the other, or maybe something different. So let me share my desktop and talk about the plan today. Okay, so here is a plan. I will start out, as always, answer any questions you might have, and not just at the beginning, but throughout the, whenever you have questions, you can pop them in the chat box. You can ask if you want on your, microphone, whatever works for you, and I'll be happy to answer. And then we're going to move into, as I mentioned, this is the second half of the class, and pretty much we're going to spend the entire second half of the class on hypothesis testing. So it's a big deal. Otherwise, we wouldn't spend the whole time on it. So this week is the initial week of hypothesis testing to get you the idea of what it's all about and why we do it. So we'll talk about the step-by-step process on hypothesis testing. It turns out you've all seen it, but you didn't hear it. You didn't necessarily hear the word hypothesis testing before. And you may not remember it, but you get it in middle school, believe it or not. And in middle school, they call it the scientific method. Have you heard of that? Hopefully you've all heard of that. And that's what hypothesis test means, that you're going to do the scientific method using statistics to back up all the things you're supposed to in the scientific method. So it's not just observing something, but you're actually going to take statistics and saying, yeah, it's working. So we're going to be looking at what's called the null and alternative hypotheses. Then we'll get into the type 1 and type 2 errors. Okay, then we'll get into the level of significance. If none of this means anything to you, that's fine. If none of it means anything to you in an hour and a half or so, that's not fine, because that's what we're talking about today. We'll talk about the p-value. We'll talk about how to state your conclusion. We'll talk about interpreting the p-value. We'll talk about interpreting the level of significance. And then we'll talk about project 2. So project 1 came and went. It was fun reading your projects, got to read them, and some of you did really well. There were some issues, but some good ones, always has it works that way. Project 2 has some similarities, but a lot of differences. The big similarity is it's still a project with partners. So that's the big similarity. The difference is it will be that because we're much farther into the class, that means that you're going to be doing a lot of statistics and inferential statistics, which means confidence intervals and hypothesis testing. And that's why I'm ready to talk about it a little bit, not fully today, by the way, because you need to know next week's stuff before you're really ready to start. But I'm going to give you kind of thoughts about it, and then next week you'll really be able to do it. So that is the plan for today. I want to stop and ask, are there any questions about anything? It's a great time to ask. Always happy to answer questions. And by the way, I should mention while you're thinking, the expected value of the lottery is positive right now. You know what that means? I hope you all do, because that was, a chapter.
Wait, so you're saying buying a ticket has a positive expected value even when factoring in the cost of the ticket?
Yes.
So we should go out and buy lottery tickets, right?
Well, here's the problem, is that it's definitely, positive expected value, but there's a very good chance you don't win, but if you win, you're a billionaire. Do you see?
Wait, so then, I mean, wait, if it has a positive expected value, that means you expect to gain. So then you should buy, right? It makes sense.
On average. So if you look at everyone in the country who bought a ticket and you look at the amount of money spent buying tickets, the amount of money returned to everyone is more than the amount of money spent buying tickets. If it's one.
Okay.
It's a little more complicated than that because it's expected value. So you take the probabilities, you multiply them by the amount you win, and then that includes the probability of losing times a -2 because that's the amount you lose. And if you add them up, you get a positive value. Now it's a little more complicated than that because that's the expected value of winnings, versus losing. There is one extra item that I'm not putting into my math, but that's called taxes.
I thought California didn't tax lottery winnings.
But I think the feds do.
Oh, yeah.
Yeah. But anyway, even with taxes, I think it's positive expected value. It's $1.2 billion. So I'm going to give a big scholarship out if I win, and more too. I don't know what to do with that kind of money. But anyway, it's a positive expected value.
Did some calculations. The one way you can increase the expected value of a lottery ticket is by opening your own store and becoming a California lottery retailer. So then you get an extra percentage of the winnings. So you essentially buy it from yourself. You get an extra percentage of the winnings.
Yeah, but what you're doing then is just you just have a business. Then you got to work.
That's true.
You got to spend hours. Don't forget.
Yeah, there's the opportunity cost.
Yeah. Expected value when you're working should always be positive because you should always be getting paid to work. So there's a question: are you keeping the same project partners or new ones for project 2? And are you picking partners? So here's the thing. I'll be talking about that when we get to number 9, but I might as well answer it now. The answer is, if you want to, you can keep your same partners. But if you don't want to, you don't have to. And of course, if you have a partner that, dropped the class, we don't have too many of those, but if you definitely want to check to make sure that your partner's still in the class, then if your partner's not there anymore, you can't have that as your partner anymore. But as long as you got along with your partner, if you hated your partner, change your partner. And make sure if you are changing partners, make sure your partners that that you used to have, let them know that you're changing partners. You don't have to say you hate the person, but just let them know you're changing partners. And then you're allowed to change partners, but you don't have to. It's whatever works for you. But it's the same rules. You have to have, recommended is a partnership of 3. 2 is allowed. 4 is not. 4, if there's 4 of you should split up into 2 groups. And maybe even find a couple more people and do 2 groups of 3. So hopefully that answered your question. And again, we'll talk about all this at the end. Other questions? Okay, so let's talk about the null alternative hypotheses. So I'd like to bring up an example that you may not have experienced, but you all know about. And I'll give my experience. I was on jury duty. Okay, and that's one of those things that once in a while you get a jury duty notice and you got to go, or bad things happen. And I got put on the jury, and we had to decide based on evidence, guilty, or they say guilty or not guilty, but that's not really what it is. It's guilty or not enough evidence to show guilty is really what it is. And the way it works is, hopefully you all know what it means to be on the jury, is you listen to the evidence, okay? And in our class, that evidence will be statistical analyses and probabilities. And then based on the evidence, you have to make a decision. And your decision, the 2 choices you have are guilty, send them to jail, or we don't have enough evidence to say they're guilty. Does that make sense? In my experience, I had one where it was a person in the back seat, and the car was moving weird, and the cop stopped them. They found a big bag of meth in the front seat. So the big question is, was the person in the back seat guilty for this big drug deal that was about to happen? So that's one of those things you have to decide. It's kind of what we're going to be looking at is we're going to have to make a decision where our decision is going to make a big difference and can cause a lot of pain or a lot of reward. And you don't want to blow it if you don't have to, but you do what you can. And that's what we'll be talking about with these kind of things. So we're going to start out with the null and alternative hypotheses. And that's like deciding guilty or not guilty kind of thing, or deciding for the vaccination, deciding whether to, if you, let's say you worked for the FDA, Federal Drug Administration, and decide whether to say, yes, this vaccination's working, we're going to let it go, it's safe, and you're going to give it to, half of America or whoever wants to grab it, which is a lot, millions and millions and millions of people. Or you're going to say, no, we don't have evidence to show that it's safe, and we're not going to be able to get that vaccination going. Okay, that's a big deal. And by the way, as you might or might not guess, it's all statistics. Okay, to me, there's other stuff involved too, but there's a lot of statistics involved in deciding whether a vaccination is approved. Okay, it's just how it works. So let me do that example. So for the vaccination example, what they did is they actually did in terms of the real thing is they did a control experiment. Do you remember what a control study is?
Isn't it where you just observe something? That's
That's called an observational study.
Oh, observational, yeah.
Yeah, control study, what they did is they grabbed around 50,000 people. Okay, it was a lot of people. And around half of them, they gave them the vaccination. And the other half of them, they gave them a fake vaccination. So they gave them a shot that had nothing in it. So they thought they were vaccinated. And then they waited a while and they wanted to see, so the group that receives the placebo is the control group, whereas the treatment's the other one. And then what they did is they said, well, in terms of if you think you're vaccinated, they said at the time, 4% of randomly selected people or unvaccinated people were getting COVID. So the big question is, if you're vaccinated, does that percent go down? Because that's what you want. For a good vaccination, you want to make sure that you're actually making it less likely to get COVID after you get the shot. Because if it's not less likely, what's the point of getting the shot, right? So this is how the symbolism works for hypothesis testing. So the first thing is we use capital H, and hopefully you can all guess why we use the letter capital H.
To not confuse it with like height, usually use
No.
lowercase h.
I'm hoping you can all guess. No, because it's the first letter of the word hypothesis. Yeah, it's for hypothesis. So H is for hypothesis. And then what they use is this little sub-zero. And unfortunately, the British got to it first. Anyone speak British? You know how to say zero in British? If you're in England? Not. Z is one way, and not is the other way. There's actually two ways. And they call it H naught. And I want to mention this right here is important. It's not an equal sign. It's a colon. So these first three symbols are always exactly the same. And that is H sub-zero, which is not, and then colon. And then the next thing you have to do is you have to say, is this a quantitative study or is this a yes-no study? So if you're thinking about the vaccination, what they're doing is they're giving everyone the shot, and then maybe, you know, and I don't know how long they waited, but maybe a month later, then what did they have to check on? Should be obvious. So they gained the vaccination shot, and then a month later, what did they check on? Last vaccine is, maybe I should tell you, do they have COVID? Or did they get COVID? And it's a yes, no question. Do you see? If they got COVID, the answer is yes. If they didn't get COVID, the answer is no. Do you see? So that's definitely a yes, no question. And when you have a yes, no question, we use the letter P for proportion. Okay, so we say P equals 0.04 because at the time, 4% of unvaccinated people were getting COVID. Any questions on that? So this piece right here, H naught colon P equals 0.04, is called the null hypothesis. Okay, that's called the null hypothesis. And it's usually used for the status quo, or what happens if what you're trying doesn't do anything. Does that make sense? So that's the null hypothesis. Then there's going to be the alternative hypothesis. That's what you're trying to show is correct. So if what we're trying to show here is the vaccination works. Okay, doesn't mean nobody ever gets COVID who's vaccinated. Okay, that's not how vaccinations work. But the first thing is we're still going to use the letter H. And then I'm writing 1 here. More often than not, you're going to see a 1 for the alternative hypothesis. Occasionally, instead of a 1, you're going to see an A. And I just see it. I see it both ways. I tend to like the 1 because then 0 and 1 look like they work together. And no one ever uses N for the subscript on the null hypothesis. They all use 0. So that's why 0 and 1 makes more sense to me. But sometimes you'll see an A because other people like A. Okay, and then still a colon. Still a P because it's a yes, no question. And the idea is we're trying to show the vaccination works. So if the vaccination works, that means the proportion of people who are vaccinated who get COVID is a smaller percent than the people who are not vaccinated. Do you see? Just regular, there's what everyone else is doing. And that's going to be less than 4% or less than 0.04. So let me ask you, any questions on this example of a null and alternative hypothesis? Okay. And is it always 0.04? Definitely not. Okay, I'm going to do one later where we're going to say, do we think that Proposition 30 is not going to pass? Okay, 4% is not what you need to pass an election. What do you need to pass an election? Over what? For a regular proposition or a candidate, that should be obvious. What do you need to win? Yeah, majority, which is over 50%. Do you see? So that'd be 0.5. So this particular one is an example of 0.04 because that's the percent that had COVID at the time. Do you see? Okay, and in fact, when they did it for the under 5-year-olds, okay, which is like getting that approved is really tough because it's a much smaller than 4% of the under 5-year-olds are getting COVID, even of the unvaccinated. So it's very different. Okay, so it won't always be 4%. Sometimes it'll be 50%. Sometimes it'll be 10%. Sometimes it'll be 73%. It all depends on what you're trying to compare. Okay, so besides P, what other letter might you see in other examples of a hypothesis test? What's the other biggie that we've had in this class? X is a good try, but not X. And the hint is P is a population proportion. We didn't use a P hat. No. Okay, the other letter you're going to see is mu. Because if you're doing a study, for example, to find out if, let's say the average worker right now works less than 8 hours a day, on a work day, then you would say mu is equal to 8 versus mu is less than 8. Do you see how that works? And that'd be mu because now it's quantitative. Any questions on P versus mu? Okay, I did notice that a few of you on the discussion assignment and also on the exam switch proportion and mean in terms of what you wrote. Make sure that if it's a yes/no question, you do not use the word mean or average. You use the word proportion or percent and use the letter P. And if it's a quantitative study, then you don't use P or proportion or percent. You use mu, mean, or average. Does that make sense? And population, mean or population proportion. Okay, so the next piece is state the ramifications of a type 1 and type 2 error. And I want to let you know, and this is important, the order at which we do things is essential. You can't change the order. Okay, first thing, if you don't know what the hypotheses are, you don't even understand what the survey is. You have no clue. Does that make sense? If you didn't write anything down, you don't know what's going on. So we start out with the hypotheses. Then we're going to do what's called the type 1 and type 2 error. Okay, type 1 error means we're going to reject the null hypothesis when the null hypothesis is true. Okay. And what I've learned is that a lot of people don't know what the word ramifications are. Who knows what the word ramifications? It's not a math word, by the way. It's English. Who knows that word in English? Again, it's not statistics. It's an English word. Yeah, it's a synonym for consequences. Yeah. All the bad stuff that might happen because of it. Does that make sense? So that's ramification. If you have an error, then bad things will happen. That's what errors do, right? So what bad things will happen if we were to have a type 1 error? So type 1 error means we reject the null hypothesis. And by the way, if you reject that P is 0.04, that means you're going to accept that P is less than 0.04. So if we're going to say, yeah, we got evidence that the proportion is less than 0.04, that fewer than 4% of those vaccinated get COVID, what are we going to do? If you're the FDA, what are you going to do? If scientifically and statistically we find out that after getting vaccinated, you have a lower chance of getting COVID. Yeah, you're going to promote the vaccine. You're gonna accept it. If you're FDA, you accept it. You don't promote it, but promote, I'll let you have it. And then it'll get promoted and it'll get accepted. And then, millions of people get the vaccine. Does that make sense? But, and this is why it's an error, when the null hypothesis is true. So they accepted the vaccine, right? And then everyone's getting this vaccination, and then P is 0.04. So in other words, 4% still get COVID. Is that a bad thing? Yeah, it's a bad thing because what happens, let's write the ramifications down. So what happens is the vaccination Vaccine gets approved, but doesn't work. People have to go through the vaccination process. Okay, I don't know about you, but after I got vaccinated, I was so tired the next day. I didn't die or anything, but I hardly got out of bed after my vaccination, especially my second shot. Okay. And it was miserable. And not only that, so we'll be tired the next day. And then be overconfident. And maybe end up getting COVID because they thought they had a smaller chance. When they didn't. Any questions about the ramifications of a type 1 error? Okay. Would this be bad if this happened? Yeah, it'd be terrible. Okay, it'd be awful. It wouldn't. This isn't killing everyone, by the way, but it's probably going to kill some people, and it's going to make a lot of people miserable. It's also expensive. You can look at it that way too. The government's got to pay for it, so that'd be terrible. They're spending all that money and it's doing nothing. Okay, now let's do what's called the type 2 error. Okay. By the way, a type 1 error for the jury duty one I talked about. What's a type 1? What's the ramification of a type 1 error on jury duty? Yeah, false conviction. You're putting someone in jail who was innocent. Is that okay? Yeah, that's horrible. Okay. So the type 1 error on the jury duty is a really bad thing because you're putting someone in jail who shouldn't be in jail. They never did anything wrong. Do you see? So there's lots of different kinds of type 1 errors. So I like to give you more than one example so you don't just say, well, the vaccination is the only one you understand. Let's do a type 2 error. Type 2 error means there's not enough evidence to reject the null hypothesis. And we say we fail to reject. I know it sounds like a double negative, but it's not quite. You fail to reject. It means you're not able to say it's not true, when the null hypothesis really was false. So now we're going to look at the ramifications of the type 2 error. So again, the type 2 error means that we were not able to reject the null hypothesis. We're not able to say that people are less likely to get COVID after getting vaccinated. What's going to happen? Any thoughts? What'll happen if you... Incorrect? Actually, we don't assume it doesn't work. We say we don't know it does work. I know it sounds like the same thing, but it's not. It means you don't have enough information to show it works. So what's going to happen is the FDA is not going to approve the vaccination. Does not get approved. But it does work. But it really does work. So why is that bad? Anyone get hurt by that? Any thoughts? Okay. Actually, you say not directly, but directly. Because there's directly people are not getting vaccinated, which means there's people going to get that COVID when we could have stopped it. Do you see? Okay, could have reduced it, which means there's going to be more people getting COVID when they didn't need to. So directly getting hurt. Do you see that? So there's a vaccination. Nobody gets vaccinated. And 1 million more people still get COVID. Still, let's try die of COVID. That's pretty terrible, right? When maybe it would have been only 500,000, right? 500,000 people just died because they didn't approve it. Do you see that? Any questions? Any questions on that? Okay, so again, step 1 was to state the null and alternative hypotheses. Step 2 is to interpret the type 1 and type 2 errors. Okay, and you're going to see in this stuff, there's a lot of writing. Step 3, and that is decide on the level of significance. And the level of significance is the probability of a type 1 error. Okay, the standard level of significance is 5% or 0.05. And in our class, maybe I'll write that down, for us, we will always use 0.01, 0.05, that's 5%, or 0.1, that's 10%. I can write 1 0 to make it look more like a 10. Okay, so those are the 3 that we'll use, and those are pretty standard. Anything can be used, but those are pretty standard. Almost every publication you'll read uses one of them. Okay, so now we got to think about what should we do? And I want to let you know there's a give and a take. So if we decrease, because we don't want a type 1 error, so if you make a type 1 error less possible, then a type 2 error becomes more possible or more likely. Versus if you let a type 1 error be more likely, then a type 2 error becomes less likely. So it's a give and take situation. So what we need to do is we need to say which is worse, the type 1 error or the type 2 error. What do you think? Okay, and so you guys say type 1. I think type 2 error is worse. It's not a statistics thing, it's a more morality thing. So again, I have one person on my side. But again, that's more morality than statistics. So what you're going to have to do, by the way, possibly like on the next exam and also the discussion, is you're going to be looking at type 1 to type 2 error, and you're just going to make your case. Does that make sense of which is worse? Personally, I think type 2 error is worse because we're talking about 1 million people still dying. Do you see that? I don't want 1 million people dying. Maybe you don't care, but I don't want 1 million people dying. Whereas a type 1 error, there might be, maybe 100 million people with like a bruised arm and feeling tired the next day. And death to me is much worse. But again, you might, think 100 million people getting tired versus 500,000 people dying. It really depends, but you have to make your case. So I'm going to make my case. I'm going to say since the type 2 error ends up with possibly hundreds of thousands of deaths that could have been prevented. It's worse. So if a type 2 error is worse, that means that you're going to make the probability of a type 1 error larger so that the type 2 error has a smaller probability. So if the type 1 error is larger, that means we use a larger level of significance. So use the level of significance. And then I want to show you the letter, see if you guys know. And I've never had anyone say yes. Anyone fluent in Greek or anyone from Greece? Never had anyone fluent in Greece. And I've been teaching for like decades and decades. And I've never had a student that's fluent. But you might know this. What's the first letter of the Greek alphabet? You got it. Yeah, when I was a kid, everybody knew because we had a store called Alpha Beta. But alpha is the first letter, and the way we show it is I got to show you with math. Insert math equation, and we go Greek alpha. So that's the alpha equals 0.10. So I'm going to use a larger level of significance because I want my type 2 error to be smaller probability, to have a smaller probability. Any questions on anything that I've done so far? Okay, on the jury duty one, by the way, what would happen with a type 2 error for jury duty if you're on jury duty on the trial? We talked about a type 1 error. What's a type 2 error do for jury duty? Yeah, false innocence. The person was guilty, but we let them go. So now we got a drug dealer that maybe gets to continue selling drugs. Okay, that's bad, right? But then you want to say, well, what's worse? Putting someone in prison when they actually didn't do anything wrong, or not putting a drug dealer in prison. Yeah, in that case, type 1 is worse. Okay, if type 1 is worse, if a type 1 error is worse, then you would use 0.01. Do you see that? Then you use 0.01 because the type 1 error is worse. Because you want the type 1 error probability to be very much smaller. Does that make sense? Okay, so if the type 2 error is no big deal and type 1 is terrible, you use 1%. Okay. And again, we won't do this in our class. There are cases where you might go to like 1/10% or 0.001. But I'm letting you go for 1%, 5%, or 10%. That way you're showing you understand it. Any questions at all on this next step, the finding the level of significance step? Okay, so once we found the level of significance, the next step is actually the step that takes all your work, all your time. Okay, but you're not going to notice that in this course because mostly you're just like answering questions from homework and stuff. But in the real world, it takes a lot of time to collect your data. So I wanted to give you a reminder, for example, if you're in this particular study, they had 50,000 people they needed to test. Okay, you can imagine how much work that is to vaccinate or placebo 50,000 people. Even to get them to volunteer would take a huge amount of effort. Does that make sense? Whereas what we're doing now is taking like an hour of work, but it's going to take like a month of work with a huge group of people just to get those 50,000 people. So you want to make the next step right. So even though it doesn't say much, that's actually the hardest step in the real world, is collecting the data. Okay, and we learned in the first week of class that in collecting the data, you want to make sure you limit bias as much as possible. Think about your survey question, think about you can do stratified sampling, all that kind of stuff. So I'm not going to get into that because we already did in the first week. And then you're going to put your data into a computer. No one does it by hand anymore, by the way. And you're going to calculate what's called the p-value. Okay. So the p-value is the probability that if H naught is correct, that you're going to end up with such a value that is far from, such a proportion or mean that's as far from the true mean or proportion as what you got. Okay, you're going to compare the p-value with the level of significance. So again, if you have a very, 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 very small probability of getting what you got, assuming H naught was true, then you're going to say that assumption of H naught is true can't be right. And you're going to say that H naught's false. On the other hand, if that probability is not that small, assuming H naught is true, then you're going to say H naught might be true. Do you see? If I flip a coin 1,000 times and get 498 heads, do you think I cheated? Right? Because you expect 500 heads. But what if I got 498 heads? Would you accuse me of cheating? What do you think? Yeah, hopefully you wouldn't accuse me of cheating, right? Unless you really just hated me or something. Okay. On the other hand, if I flip, because the probability of getting 498 heads is not that small, 498 or less is what you usually say. On the other hand, if I flipped a coin 1,000 times and got one head and 999 tails, do you think I'm cheating? Would you accuse me of cheating? Yeah, you should accuse me of cheating because that just shouldn't happen. Do you see? It's possible to happen, but it's not even 1 in a trillion chances of happening. Do you see that? So that p-value, that 1 in a trillion chances, if it's really, really small, then you're going to say, cheated. H1 is correct. Okay. If the p-value is not that small, maybe it's 0.4 or something, then you're going to say, well, it might be cheating, but probably not. I don't know. Do you see how that works? You're not going to make the accusation. Here's the picture of what happened. The p-value for the original vaccination. Okay, this was a couple years ago they did this. Okay. It was mid 2020, was 1%. I'm sorry, that not the p-value is 1%. The proportion of people who got COVID after the vaccination was 1%, which is definitely less than 4%. And you look at this number, and it turns out that this area was small. And the p-value that they got when they did the 50,000 person test on the vaccination was 0.004. So we were using 0.01. Okay. And by the way, had you even used using 0.1, had we used 0.01, it still would have been smaller. But the p-value is definitely small. Do you see that? When that p-value is small, that means it is very unlikely that the vaccination had no effect and the people just got lucky and didn't get COVID. Do you see that? Even though it could happen. But when you have 50,000 people not getting COVID, or only, you know, 0.4% getting COVID, then that tells you, or sorry, 1% getting COVID instead of 4% getting COVID. That tells you the vaccination is working. Do you see that? So then they were able to say there was statistically significant evidence. And this is how you conclude. This is stating the conclusion. So if I ask you to state the conclusion, this is how you state the conclusion with this example. There is statistically significant evidence. I put it in red because those words have to be there. Okay. By the way, on your discussion post, if you don't put there is statistically significant evidence, if you reject the null hypothesis, what's going to happen? Yeah, I'm going to take off points. That's a promise. Okay. So make sure that you get that in there. That's when you reject the null hypothesis, when the p-value is small, very small percent that the null hypothesis is true, you say there is statistically significant evidence to conclude that the population, notice, just like confidence intervals, this word population is really important. It's not the sample that we're looking at. Now we're looking at everyone who could ever get vaccinated instead of the people we vaccinated. That the population proportion of vaccinated people who get COVID is less than 0.04. Okay, now because of that, what did the FDA do? Again, this is a real life thing. This really happened. What did the FDA do? Thoughts? Yeah, they approved it. Okay, and hopefully you all know that the vaccination got approved. And it wasn't because someone paid the FDA off or anything. Okay, they really did this. And then there were multiple other in other countries where they found the same thing. Okay, so then it's really, you know, so even if you thought that our FDA was somehow corrupt, well, the one in Germany wasn't, you know, it's not like everyone is going to be corrupt. So if they're all saying it's true, then it's true. Do you see that? Okay, by the way, what do you think I did after it got approved? What do you think the first thing I did after it got approved? Any thoughts? Nope, I didn't get the vaccination. I'm not a doctor, so I couldn't. They gave it to the doctors first because remember, then they had to go make the vaccination. So I couldn't sign up for the shot yet either. Okay, I bought Pfizer stock. No, because it was too late for that because it already went up. I looked at the statistics. I went to the report, okay, and I looked at the data and I calculated the p-value to double check because I like to do that because I'm a statistics instructor. And hopefully you guys can do that too because now you will have taken statistics. And I looked at the statistics and they really did it right. Does that make sense? So it got approved and I looked at the p-value and it was what it should be. Does that make sense? Okay, here's what you shouldn't do. You shouldn't just go to Facebook and look to see if there's some or Twitter and see if there's tweets about it being bad because that's not scientific at all. Instead, look at the data, see if it worked. Does that make sense? Okay, and then about a month or two later, they opened it up to educators and I was able to get my vaccination. Okay, and by the way, I'm double boosted now. Actually, I'm double boosted. So I've gotten 4 shots. So because but I always look at the statistics and make sure the p-value is small before I get it. Okay, and they do their job. That's the good news. Any questions on this as like a real life thing? This is important. Okay, if they didn't do a hypothesis test for the p-value, I would not have gotten the vaccination. Okay, there was one time in my life when I did take a drug before it was approved. Any guess? All right, do you want to guess? I was a college student. There was a an advertisement in our little college newsletter saying, if you have the runs, run to the hospital, get $100 to be part of a study. So I was actually one of these people. And the really bad news is I was not in the treatment group. So the doctor apologized the day after when I didn't get better and then gave me real medicine. I was in the placebo group. But they gave me $100. So that stuff happened. So I was actually I got to experience how this stuff really works. Okay. Which wasn't happy because I had the runs for another day. Wasn't fun. I didn't die, but obviously. But anyway, so I've been involved in that on the opposite side. Okay, any questions? Any questions on this? Any questions on this example and how the process works? Okay, so this is hypothesis testing. When you have to make a decision, you do a hypothesis test. Okay, confidence intervals are not for decision making. What are confidence intervals for? Because they're different than hypothesis tests. Do you remember? That was last week, but it's not that long ago. What percent confidence? Yeah, so it's for approximations. If you want to get an approximation and get an idea of how far you might be off, then use a confidence interval. But if you have to make a decision like FDA approval kind of thing, then you do a hypothesis test. Okay. All right, so here's another one. Okay, and again, I don't know where all you are from, but I'll tell you, if you're from Tahoe or you know a lot about Tahoe, then you know our number one big thing when it comes to any science is our lake. And we want to make sure that our lake stays clear and nice and good. Put it in a chat box. Have you been to Lake Tahoe? Yes, no? Okay, so you're all saying yes. So then hopefully you all believe me and agree that Tahoe is beautiful. And we don't want it to get ugly. Okay, and terrible. Okay, so one of the things I actually do, I'm on a different side now, is we have something called Snapshot Day every year, where a team of volunteers, and I'm one of the volunteers, I'm not the statistician. I have been the statistician on this, but lately I've been the volunteer. And we actually go and we test the lake. We test the water that goes into the lake. And one of the things we test a bunch of things, and one of them is the pH. You probably all heard that before in chemistry, right? Okay, so we test the pH. pH of 7 is like pure water. So the question is, does the average pH in streams that flow into Lake Tahoe differ from 7.0, which is water? Does that make sense? Okay, so now I'm doing this because this one's going to look a little different. H naught, we have H naught colon, that's the same, but here's the new thing. Hopefully you all remember how to pronounce what I just highlighted. What is that thing after the H naught colon? Yeah, that's mu. Okay, that's mu. And I want to mention something, this is important. I do not grade off on your exams or on your discussion replies and posts if you type MU instead of get fancy and try to figure out how to make alpha come in. So I don't grade on whether you can do like computer programming to make it look pretty. Does that make sense? I do want you doing on projects because then you have a group of people, you can get help from us, you have lots of time, so then you should make it look like a mu. But for all the other stuff, it's okay if you just do it kind of, MU instead of the letter. But this is mu, and it's mu because what we do is we use a pH reader. And then, I don't know if any of you ever done a pH reader? Used an instrument that calculates pH that shows it? Okay, some of you have. Okay, and it does not say, yeah, one of the strips actually is a little harder. The one we use actually is much better than the strips. The strips is like old fashioned. So the pH reader we use now is we put an instrument into the water and it tells us the pH. And that might be, 6.21. And the important thing is it gives you a number. Yeah, in a clinical setting, you can use it, but for good, really good science, it's much better to have a number than like, does the color look about right? Does that make sense? So numbers are better. Okay, maybe because I'm a statistician. But what we use is something that gives you a number, and the important thing is you get a number. And because you get a number, it's a quantitative study we're talking about. Got it? And because we have a quantitative study, we're using mu. We're not using p. You will lose points if you use the wrong thing. Okay, if you write p instead of mu or mu instead of p in the situation you're asked to do. Okay, so make sure that you get that down. That's a big deal. Okay, so we're gonna have mu equals 7. So now, if mu is, by the way, really low, if mu is say 4, or let's say mu is 11, either way, it's horrible. Okay, and again, you're not required to understand chemistry, but hopefully you'll trust me. If you have a pH that's really low or a pH that's really high for the pH of Lake Tahoe, then that's a bad thing. So what we're going to do is we're going to do what's called a two-tailed test, which means we're going to use a not equal to sign. Okay, and as I mentioned, if you don't want to have to try and figure out how to make not equal to happen on a computer, you can use NOT and then the equal sign. That's fine too. But since I know how to do it, I use a not equal to sign. So this is called a two-tailed test because if it's either on the high side or the low side, let's say the low side or the high side, so it'd be the left-hand side or the right-hand side of the normal curve, then you're going to reject the null hypothesis if it's far on either side. That's the two tails. Do you see? Any questions on that? Because we don't want the pH to be far from 7. So either tail is bad. Does that make any questions on that? Okay. So if there's a type 1 error, again, that means you reject the null hypothesis when the null hypothesis was true. What are the ramifications of that? What bad things happen if you're the science group and you ended up with a type 1 error? Any thoughts on what the problem with that is? All errors are bad, so what goes wrong? What bad things happen in this example? Thoughts? Not seeing y'all jump in. Okay, example. Okay, you're going to conclude that it's not 7. Okay, and what are you going to do?
You might try treating the water with something if you think that it's like not 7 pH, like not just true pH what it should be. So you might end up adding something that shouldn't have been added.
Okay, right, that could happen. You might do some water treatment. Let me tell you, because I live here, tell you what would really happen and what has happened. No, not with the type 1 error, but because they rejected the null hypothesis, is that you're going to have all kinds of laws and rules and spend a lot of money on mitigation. So many rules or regulations will be put in place And millions of dollars will be spent to get that lake pH back. Okay, your idea of going and throwing an acid if the pH is too high, sounds good, but that doesn't happen. But that you can imagine it happening, but that's not what happened. This is what happens. Okay, there's huge rules. There's going to do all kinds of stream water changes and stuff like that to keep bad stuff flowing in. Huge amounts of effort. Okay, and that's bad, right? All right, but now let's go to the type 2 error. Okay, that means you fail to reject the null hypothesis when the alternative hypothesis is true. Why is that bad? What happens? So what are the ramifications of a type 2 error? Yeah, nothing's going to be done, and the water is going to get worse and worse and worse. So no regulations occur. But the flow into the lake ends up harming it severely. And we lose our beauty. Right? Does that make sense? And all of a sudden, Lake Tahoe starts smelling bad. It looks awful. You don't want to swim in it. Nobody wants to come to Lake Tahoe. It's just awful. Animals die, the fish all die. All kinds of bad stuff can happen. Okay, which is worse? Yeah, that'd be Tahoe's worst nightmare, right? Now, for me, I live in Tahoe. Type 2 error is definitely worse. Okay. Okay. On the other hand, if all you care about is money, then maybe one is worse. Do you see? So again, the most important thing is you have a good argument. Okay. Any questions on that? Okay. If they're the same, you do 0.05. If the one is worse, you do 0.01. If 2 is worse, you do 0.1. Okay. I think type 2 is worse. So then I'd use 0.1. Okay. And if they get a p-value, let's say they got a p-value of 0.27. Does that mean if you get a p-value of 0.27, which is greater than 0.01, does that mean that the lake has no issues? The pH really is 7? What do you think? Yeah, it doesn't mean that at all. It means one of two things. Either the lake's pH really is 7, that's possible. Or it might mean your sample size was too small and you weren't able to get a smaller p-value because you didn't do enough samples. Do you see that? And the lake really, and it really is a problem, but your sample size is too small. Any questions on that? And that's why you never, ever, ever accept H0. You never say H0 is true. You only say we don't have enough evidence to say whether or not H0 is false. You see how that is? Could be that H0 is true, or it could be that you just didn't do enough studies, didn't do enough sample, not big enough sample sets. Any questions on that? All right, so let me write down first thing. is the conclusion is there is insignificant evidence. So you'll say insignificant, sometimes you'll say insufficient. To make a conclusion. That the pH for all streams into Lake Tahoe, all right, LT for Lake Tahoe, is not 7. Okay, and let me write the population mean, because we need those words. Any questions on that? All right, so what does it mean to have a p-value of 0.27? So this is there's no way to write it in a short way. So here's what I'm going to write. So if the pH of Lake Tahoe is 7, and let me write the population mean pH of, let's write streams into Lake Tahoe is 7. And if we did another study of, and I don't know if I told you how many, let's say last year, actually, there were about, I think there were about 45 of us doing this, 45 groups of 45 samples. Then there would be a 27% chance. See the 0.27 right here? That's our p-value. That's a probability. P stands for probability, by the way. So there'd be a 27% chance that the pH, sample mean pH for this new study would differ, and let me write this way, would be, so the X bar that we got was 6.4. By the way, is 6.4 less than 7? Is 6.4 7? Is that the same thing as 7? Right, it's not the same as 7, but you're never going to get, almost never going to get exactly your H naught. But the question is it far away enough? And in this case, in terms of this new study, the pH for this new study would be either less than 6.4 or greater than 7.6. Where did I get the number 7.6? And don't just say from the picture. Our X bar was 6.4. Where did I get 7.6? How did I get that number? Yeah. So the idea is we're doing a two-tailed test. So 6.4 is on the left side, and it is 0.6 away from, it's 0.6 to the left of 7. Because 7 minus 6.4 is 0.6. So if I go 0.6 to the right of 7, I get 7.6, 7 plus 0.6. So that's how I got that 7.6. A lot of people have trouble getting that second number. But when you're doing a two-tailed test, it's both sides that matter. Any questions at all on this, understanding this p-value? What does it mean to have a p-value of 0.27? Okay, now let's interpret the level of significance. Here's the good news. I can copy and paste. So since this is an online class, you're going to be doing all your stuff on computer anyway. So you do the same. I can copy and paste everything up to the word A. I want to interpret the level of significance, and I'm going to say if the population mean pH of streams into Lake Tahoe is 7, and if we did another study of 45 samples, then there would be A. Okay, now I used a level of significance of 0.1, so 10% chance that the new study would falsely lead us to conclude that the population mean pH of water flowing into Lake Tahoe differs from 7. So that's kind of the way of saying that there'd be a 10% chance of a type 1 error if the mean pH really was 7 and we did the study again. So let me ask you, are there any questions about these very long interpretations? Because you're going to have to do this, by the way. So make sure you get this down. Okay, so let me move forward. And I'm going to do this pretty quickly because we only have so much time left. Suppose you want to see if women are not drinking the recommended 2.7 liters per day on average. Okay, that's what they recommend. Then you would say H naught is mu equals 2.7. H1 is mu is less than 2.7. Do you see? Because if you think they're not getting enough water, that means it's less than. Suppose we decided on a 0.01 level of significance. So I'm going to pretend we already did the type 1 and type 2 error. What I want to do is I want to show you how to use a calculator. Here's the data that was given that they found. So I'm going to grab this data. I'm going to copy it. And as you might guess, I'm going to go to the calculator. Sound good? Which calculator do you think I'm going to go to? What number? What number calculator? Hey, if you guessed, you have a 1 in 25% chance. 15 or 14, it's 15. I have data. Do you see? I have data, so it's 15. If I were given the mean and standard deviation, then I'd have statistics and it'd be 14. But I have data, so I'm going to click that one. I'm going to copy and paste the data in. I want to give you a big heads up. Make sure you separate every number by a comma. And if you have big numbers, don't use commas to write the number out. So if you had 100,000, don't write 100, comma 000. Just write 100,000, because that's a mistake I see people make sometimes. Okay. All right. We don't know sigma, so you can leave that blank. Notice you have 3 choices. R H naught had a lesson. Our mu naught is our number from H naught, which is 2.7. So I'm going to put that in right here. And then I just hit calculate. Okay, and I want to give you a few notes. This is X bar, this is standard deviation, sample standard deviation. It's a test statistic. It's a T statistic, we call it. So if I ask you for what is a test statistic, in this case it's T, because you have to use a student's T distribution because we have to use, we don't know the population standard deviation. And our p-value is about 0.03. Any questions on that? So now I can go in and say our p-value was equal to 0.03. And by the way, we're using a 0.01 level of significance. So that means there is statistically insignificant evidence. To conclude that the population mean amount of water, and I think we just said fluid, drinking, women drink is less than 2.7 liters. Any questions on that? Any questions? Okay, so this is an important example where it's insignificant. Does that mean women are drinking 2.7 liters? They're drinking enough? Yeah, it doesn't mean that. And in fact, our p-value was pretty small. Do you see? Not small enough, because 0.01 is small enough. When your p-value is small, but not small enough, then you say, well, maybe it's just that we didn't survey enough. Do you see? Okay, we just didn't get enough. We didn't survey enough women, so maybe that's the reason. Does that make sense? So if your p-value is small, but not small enough, then you would say it's probably worth it to do another study with a larger sample size to see what's up. Any questions on that? Okay, here's what you can never do. You can never just keep doing the same study with the same sample size until you get lucky. Because then eventually you'll get a type 1 error. Even if it's if it's equal to 2.7, you'll get a type 1 error, and then you'll end up saying that they don't drink enough. Do you see? So you have to make the sample size much larger if you're going to do it again. Any questions on that? Okay. If I got a p-value instead of 0.03, what if I got a p-value of 0.93? Do you think we should do another study? Any thoughts? Because you still fail reject. But if you got 0.93, you'd say, well, I was probably just wrong in the first place. You can't say I was wrong, but you would say it's not even worth my time anymore. Do you see that? Because I'm so far off. I like to use an analogy I like to use is imagine you're the coach of a soccer team. Okay. And there's 5 seconds left in the game, and you are losing 7-0. And your player goes to kick the ball, gonna make that, that player is gonna make the goal, but the other team runs into the player falls down, time's out, and the referee doesn't even notice. Do you yell and scream at the referee because the referee didn't notice and didn't call a foul? What do you think? Any thoughts? Hopefully, you don't need to yell and scream at the referee. If you're losing 7-0 and there's 5 seconds left in the game, there's no reason to yell and scream at the referee. You've lost. Do you see? Even had the referee called the foul, then it would be 7-1. You still lose the game. Do you see that? So that's kind of what we're looking at when we're talking about these hypothesis tests. Is if your p-value is really high, it's just time to give up. Don't complain. Don't spend the effort trying to think that maybe you were right, because it's not worth it. Does that make sense? On the other hand, what if it was instead of 7-0, what if you were down 6-7 and the same thing happened? Then do you think you might say, hey, referee, you need to look at the video? What do you think? Yeah, then it's worth complaining, because then had the referee, then you think you really should have won the game, or at least tied, right? In that case. Okay, what if it was the opposite? What if it's the same thing, 5 seconds left, and your player goes to kick it, and you're ahead, say 2-0, and the other team knocks your player down? Do you yell at the referee? There's 5 seconds left in the game. Right? And the answer is there's no reason to. You won the game. Do you see? And if you win, there's no reason to yell. So if the p-value is, say, if your p-value is, let's say, 0.001, you're not going to do another test, because you're able to reject the null hypothesis and you've got what you wanted. Do you see how that works? In your project, you're going to have to talk about that, by the way. Okay, whichever situation you might be in. And there's really 3 situations. Just a note, again, I don't have a lot of time, but this is a template. So this is a template of statistically significant evidence or not. So if you reject the null hypothesis, there is statistically significant evidence to support the claim that the population will either be mean or proportion, and then whatever it might be. Does that make sense? So is less than 3.7 or whatever it might be. Okay, whereas the main difference is right here. If you have a large p-value, there's statistically insignificant evidence just to support the claim that the population mean or proportion, whichever might be, is whatever. So those are some templates. Similarly, the p-value template is if the null hypothesis is true, and if another sample of however many what your sample size was taken, then there would be whatever your p-value was, probability, and then the results of the new study would be at least as extreme as the results of this study, but that is going to be, worded differently depending on what your study is, because you have to talk about the study. And similarly, for the level of significance is if the null hypothesis is true, which of course you're going to need to write down what it means for the null hypothesis to be true. And another sample of however many it was, your sample size is taken, then there would be whatever probability it was that the new study would result in falsely concluding, and then whatever the alternative hypothesis states in words. So those are good templates. Okay, and I want to remind you, if you can't write it by the time I'm finished, this is recorded. So you can always go back and look. So here's a current event, as in like this week current event. By the way, based on this, any guess on what I did just before class? About a half an hour before class started, before I opened this up, given that reading this example? Yeah, I dropped off my mail-in ballot. And by the way, I do encourage any of you who are eligible to vote. It's a good thing, doesn't hurt. So I vote. I've never missed a voting. So I dropped off my vote, and you're allowed to vote early now. So I just did it. That way I don't have to worry about it again. Okay, and the question is, do the majority of California adults plan on voting against Proposition 30? Okay, so run a full hypothesis test. Any questions on the question? Okay, so H naught is P equals 0.5, because the word majority, if you don't have a majority, the highest you can have without a majority is 50% exactly. Does that make sense? H1 is that P is greater than 0.5. Notice not 0.51, because Can you still have majority if you're not at least as big as 0.51? The answer is yes. And I'm actually an example of it. When I ran my first election, I did not get 0.51, 51% of the votes. I got about 50.02% of the votes. I won by like 3 votes. Okay. So just over 50%, but not like much of any over 50%. But I still won. So don't use 0.51. It's P is greater than 0.5. Got it? Okay. By the way, you would use 0.05 on use the 5% level of significance on this one, because pretty much this is kind of new stuff and they always use 5%. So here is the survey. And if I go to that site, they actually go through and they talk about all this stuff. And they did a survey and they found out that only 41% think that this is are gonna vote for it. Okay. So only 41% said yes. Okay, which isn't a high percent. So what I'm going to do is I'm going to go to the calculator really fast. And this time I'm going to do a hypothesis test for a proportion. We're talking proportions. Our N, by the way, in here it tells you it was 1,715 is a survey. Our X, so again, we're looking at 41% said yes. So if I go to the scientific calculator, 0.41 times 1715 is about 703. I'm going to round because you can't have 0.15 votes. 703. Our P naught. Okay. What that is 0.52. Because that's what, sorry, it's 0.5 because it's the H naught piece. And we're going to calculate. So is the p-value 4.27 about? What do you think? Okay, so I want to give you a heads up. It can't ever be 4.27 because P is a probability. Probabilities can't be bigger than 1. It does not mean the calculator made a mistake. It meant that you didn't look over here and see E negative 14. Okay, and that's common, by the way. So I want to give you a heads up. This is a typical mistake people make. So it's actually 0.0000000000000. Might be one more 0 and a 4, basically almost 0. So the p-value is as close to 0 as it gets. Okay. So if we wanted to, so that means we have less than 50%. Make sure I did this right. We want greater than. So if you want greater than, and hit calculate, then the p-value is almost 1. So is this going to win, by the way? Doesn't look like it. Does that make sense? Yeah, it doesn't look good. Okay. Just a note. All right, so here's a secret word. We're not quite done yet because I want to talk about project 2, but I want to give you the secret word. Secret word is another. And that's because when you're looking at the p-value, you're saying that if the null hypothesis is true and another study was done with the same sample size. That's why I'm using the word another. So that's your secret word for this thing. And I want to mention, I want to talk about project 2 and not fully. We're going to talk about it more next week too, by the way. So you're not quite ready to do it, but you're ready to start thinking about it at least. So first thing is if I go here. And I go to project 2 requirements. As I mentioned before, you still need to have partners. And this is not project 1. I want to highlight that. This is not the same as project 1. It's a very different study. Project 1 was all about really understanding sampling technique, stratified sampling or cluster sampling, all about understanding bias, all about understanding all the different statistics. Project 2 is the newer stuff. What did we do last week and this week? What are the 2 main things we did? Someone asked which calculator, sorry, I didn't see it. Which calculator I just used. And that was population proportion. The hypothesis test for proportion was the calculator, by the way. Yeah, confidence intervals and hypothesis testing. So this project, most of your write-up needs to be about the confidence intervals and hypothesis testing, and not about all the other stuff that we did in project 1. Okay, so that's most of what I'm going to grade is about, those 2 things. You are going to mention how you did the study, but the main 2 things are confidence interval and hypothesis testing. Okay, so you are going to come up with a hypothesis. Okay, and I want to let you know it's going to be referred to what we're going to do next week. And that is you're actually going to do a comparison study between 2 different means, 2 population means, which we'll be doing next week, by the way. So that's why you're not quite ready yet. But at least you can get the ideas of it. Okay, so you're going to be doing a hypothesis test, and you're going to be doing it in the same order that I just talked about. So after getting a partner, the first thing you need to do is decide what your hypotheses are. Decide what you're interested in, what your H0 and H1 are going to be. Does that make sense? Then, after deciding what your H1 and H0 and H1 are going to be, and maybe thinking about how you might do your study, any guess on what you're going to do next? Yeah, check to see if it's okay. You're going to post on the project 2 discussion board. So to make it go faster, I'm going to do it this way. So here's the project 2 discussion forum. You're going to click on that. And you're going to hit reply and post your idea. Okay. You can also post, hey, I need a partner. My partner's not in the class anymore. You know, I want to work with someone else or whatever it might be. But you can also post that. Good place to find partners. So you're going to post on the project 2 discussion board. I'll let you know if it's going to work or not. Okay. Then once you've done that, then you are going to think about what are the ramifications of a type 1 and type 2 error. Okay, just like we just talked about today. What are the ramifications of type 1 to type 2 error? What will your level of significance be based on that? And you can actually do that part of the project. You can do the full write-up of that before you even get your data. Because you're supposed to do that before you even look at the data. Does that make sense? Then after you do that, then you get your data. And I want to let you know, this is not project 1. You don't have to do a survey of people. You could collect data experimentally. You could collect data online. Just a couple notes. If the population size is not big, this won't work. Okay, your population size must be much bigger than the sample size. And the sample sizes must be bigger than 30 each. Remember, you're doing comparison studies. So if you're doing, say, men versus women, 30 each. Or if you're asking, if you're looking at 2 outcomes of an experiment, then there should be over 30 for the first outcome and over 30 for the second outcome, whatever you're doing, just to let you know. Okay, so then you're going to collect your data, and you can do a survey. Okay, and you don't have to do the fancy kind of stratified sampling. You just have to admit what you're doing. You don't lose points for having a lot of bias. Okay, but you lose points for just not saying what you did. Just say what you did. And then you're going to put it in the spreadsheet. And I'll show you that next week, because we're not quite ready for that yet. And then you're going to do the full analysis. You're going to analyze the confidence interval. You're going to analyze the hypothesis test. You're going to analyze the p-value. You're going to analyze the level of significance. You're going to analyze the type 1 and type 2 errors. You're going to all the different things, levels of confidence. And you can do all those analyses. And just like project 1, you're going to imagine having a client, so that you having a client is really important. So you're going to imagine having a client, and then that way you have an audience at which you'll be giving this project to. Does that make sense? It actually makes it easier to have a client. And then throughout the paper, just like in project 1, but in this case, all the different things are going to be about confidence interval hypothesis tests. Throughout the paper, you're going to talk about what decisions the client is going to make after seeing that piece of the hypothesis test or that piece of the confidence interval. Any questions on that idea? The standard error, just like in project 1, the standard deviation was a huge part of the project. Here, the standard error is important in the project. I have a video for you to watch. I'm going to let you watch that on your own. And it talks about the standard error in case you forgot. That came for the central limit theorem chapter. That was chapter 7. And that's going to be a whole paragraph of your, or throughout the project, you're going to be writing about the standard error. And I'll let you read through all of these things, but it's basically what I just talked about. Okay. Any questions about project 2? And we're going to talk about it more next week, by the way, because it involves a difference between 2 means, and we haven't had that yet. So you're not quite ready yet, but you are ready to make sure you have the partners. So I do see someone has put in the chat box looking for partners. So maybe you can add them in if there's only 2 of you. Or if you're alone, say, hey, I need you to. Let's be partners. Okay, I'm going to stop the share and also stop the recording. Because there's a lot to talk about today. It went a little longer than usual. And I'm going to stop the recording.